In this lecture, we are going to discuss about the techniques to improve the quality of service. So we just saw about different flow characteristics with respect to these things, that is reliability, delay, jitter, and bandwidth, right? So now we are going to discuss about what are the different techniques which are available to improve this quality of service. Okay. So there are different types of techniques. So we are going to discuss about four important techniques to improve the quality of service. The first one is scheduling. The second one is traffic shaping. Third one is resource reservation. And the fourth one is admission control. Okay. So let us now first discuss about scheduling. So what is scheduling actually? So well, let us say we consider a switch or a router like this. Okay. So packets comes from different flows, that is to this incoming interface to this particular router. Okay, so these packets arrive through these interfaces, and whenever these packets arrive to this router, now the router tries to processes these packets. So what would be a good scheduling technique here? So a good scheduling technique can be whenever this router treats all these different flows of packets in a particular manner or in an appropriate manner or in a fair manner. That could be a good scheduling technique, right? So there are different types of scheduling techniques available to improve the quality of service. So here we are going to discuss about three important scheduling techniques. The first one is FIFO queuing, the second one is priority queuing, and the third one is weighted fair queuing. So under scheduling, we are going to discuss about these three important queuing techniques. So let us now first discuss about the FIFO queuing. So FIFO, which is nothing but first in, first out queuing. Okay. So here what actually happens, the packets wait in a buffer or a queue. This is our queue. So packets wait in the buffer until the router is ready to process them, isn't it? So this is our router when packets are coming through the incoming flow. Now these packets, the packets coming in this flow, they wait in a buffer until our router is going to process them. Okay. So if the arrival rate of these packets, that is if the arrival rate average arrival rate of these packets is greater than, or if it is higher than, the average processing rate of that particular router, that is the processing capability of the router is less than the average arrival rate of the packets, or if the average arrival rate of the packets is greater than the average processing rate of the router, then what actually happens, the queue will be obviously filling up. So what will be done? Obviously, the packets, the new packets which are coming to be processed by the router will be discarded, isn't it? So this is what we represented in this diagram. So the packets arrive from the different flows, and if the queue is full, when will the queue be full? Full when the average arrival rate of these packets is greater than the processing capability of the router, then the queue will be full. That is when the router is going to process, each and every packet will be removed from the queue and it will be processed, right? So if the processing capability of this router is less than the arrival rate of these packets which are filled in the queue, then the queue will be full. So if the queue is full, if it is yes, the router discards the packet. Okay. And if the queue is not full, that is if queue is not full, then we fill these packets in the queue, and these packets will be given to the processor, that is for the router to process them, and after processing they are going to depart from that particular router. Okay. So this is how a FIFO queue processing or FIFO scheduling is going to be done. Okay. So is this clear? I hope, right? Next, the second one is priority queuing. So if you see here, in this priority queuing, packets are assigned some priority. So if you see here, the packets arrive from the particular interface, that is from a particular flow. Now we have a classifier here. So this classifier is going to classify the packets into two categories basing upon their priority class. So this is one priority class and this is another priority class. Okay. So this priority class is a high priority class and this priority class is a low priority class. Now, the high priority packets will be kept in the high priority queue and the low priority packets will be kept in the low priority queue. So, after putting them in the appropriate or respective queues, the packets which are in the highest priority queue, this queue, are processed first. Okay, and then after completing all the packets in this higher priority queue only, then only the processor or then only the router processes the packets in the low priority queue. Okay, so if you see here, if you compare this particular priority queuing with respect to FIFO scheduling, okay, obviously the priority queuing performs better when compared to FIFO. Why? Because if you see here in the FIFO scheduling, let us say the processor or the router is processing the packets basing upon first in first out. That is, whenever whichever packet comes first, that packet will be processed. Let us say now the queue has been filled. Let us say now a packet number 10 came here. So if we assume that this is a higher priority packet, okay, but even though this is a higher priority packet, it should be compulsorily processed. But as the queue is filled now, okay, if the queue is full, obviously this higher priority packet will be discarded. Okay, so if you compare this FIFO queue with priority queuing, the priority queuing is providing a good quality of service. Why? All the higher priority packets will be placed now in the higher priority queue, and all the lower priority packets will be placed in the lower priority queue. So when a higher priority packet comes here, it is placed in this particular queue, and first of all, the processor or the router is going to process all the packets in the higher priority queue only. Until and unless the packets in the higher priority queue are completed, then only the lower priority queue will be started processing. Okay, so if you see it, the switch or the router or the processor turns to other queue only when the current queue is empty. Okay, let us say initially it is processing the higher priority queue. Only when the higher priority queue is empty, then only the processor turns back to process this lower priority queue. Okay, so then what is the drawback of priority queuing? If the system is getting all the higher priority packets, let us say initially there are how many places are there? 1, 2, 3, 4, 5, 6, 7, 8. So initially let us say we got 8 higher priority packets. Okay, they are placed in this particular queue, and then we got 8 lower priority packets, and then they are placed here. Okay, so initially the system starts serving the higher priority queue only. So when it is processing the higher priority queue, let us assume when it completes the first 3 and it got some other 3 packets, that is these packets here will shift to this place and the new 3 packets will come here. So as the switch has to or switch or router has to process and it has to complete all the packets, then only it can go to lower priority queue. So when there are only higher priority packets coming all the time, okay, now what actually happens, the lower priority queue will never be served here. That is, the packets in this lower priority queue will not be processed by the processor. So now this kind of situation is what we are going to call it as starvation. That is, the packets, okay, in this lower priority queue will starve for the processor, okay, to process them. Okay, so this is the main drawback of priority queuing. Okay, that is, if there is a continuous flow of high priority packets, then the packets in this lower priority queue will never have a chance to be processed. So this is called starvation, and this is the problem in priority queuing. So we have a third kind of queuing technique, which is nothing but weighted fair queuing technique. So here also we have different types of classes. That is, whenever the packets arrive through a particular flow, now the classifier classes the packets into different queues. That is this one, Q1, Q2, and Q3. But the difference between this priority queuing and weighted fair queuing is that, so here each and every queue is given some weight. Okay, so let us say this is the first priority queue, and let us say this is some second priority queue, and let us say this is the third priority queue. So if you see here, the weight is given 3 here, and here weight is 2, and here weight is 1. So here packets are processed in the round robin scheduling algorithm. What is round robin scheduling algorithm? Let us say there is a process P1 here, P2 here, P3 here. So first of all, the processor processes the process P1 for some amount of time, and then it goes to second process, and it processes this process for another amount of time, and here again it goes to process 3, and after process 3 it again comes back to 1, and then again 2, and then again 3. So the amount of time it spends at each and every process is called time quantum. Okay, so we'll fix the time quantum, whether it is 1 second or 2 seconds or 3 seconds. This is called time quantum. Okay, so if you see here the weight specifies that this processor has to process only 3 packets at a given amount of time. Okay, and here it has to process 2 packets, and it has to process 1 packet. So after completing this one, again it has to reach to the first queue, and then it has to go to the second queue, and then it has to go to the third queue. So like this, it is going in a round robin kind of fashion. So here we have weights for each and every queue. So this is the reason we kept this as weighted fair queuing. So it is so here there is no starvation, because the processor is going to process the first queue, and then the second queue, and then the third queue. So according to the priority, we are going to assign the weights. If this is having higher priority, we will be processing more packets here, and with some lower priority, 2 packets. With even more lower priority, we will process with the weight one. Okay, so this is how weighted fair queuing is going to work. Okay, so with this, we have completed the first concept called scheduling. Okay. Now let us look after the second technique to improve the quality of service, which is nothing but traffic shaping. Okay. So in traffic shaping, we are having two different types of mechanisms. Okay. What is actually traffic shaping? So traffic shaping is a kind of mechanism which is used to control the amount of traffic or the rate of traffic sent to a particular network. Let us say this is a network. Okay, so the traffic shaping mechanism is going to shape the traffic which is being sent to the network. Okay, so two techniques are there which can shape the traffic. The first one is leaky bucket and token bucket traffic shaping technique. Okay, so let us now first see about each and everything. So if you see here, leaky bucket algorithm, let us take an analogy of we have a bucket here, okay, and it is having a small hole. Okay, so this is the tap which is filling this bucket. So if you see here, irrespective of the speed of this particular tap, okay, so with what amount of speed it is releasing its water, it is producing the water. Okay, the leaky bucket, that is the bucket with the uh, small hole on the bottom, is going to give only one drop at a particular amount of time. Okay, so whether the flow from the top tap is whether it is speed or whether it is slow, it doesn't matter for this leaky bucket, because it is having only a small hole, and from the small hole only at a time only one drop can come. Okay, so even though, so if you take this analogy as a network, okay, so I'm just clearing this one. So if you take this analogy, this is our sender. Okay, so this is our network. Okay, so this leaky bucket algorithm is going to shape this particular bursty data, and it is going to send the fixed flow of data. Okay, so if you see it, so I'll tell you an example here. So if you see here, we looked at different types of traffic profiles, that is constant data, variable bit data, and bursty data, right? So if you see, in the starting 2 seconds, the sender has sent 12 Mbps. Okay, that is 12 megabits per second, means for 2 seconds it is 24 Mbps, isn't it? And for next second, and here, and here. So how many seconds here? 1, 2, 3, 4, and 5. For the next 5 seconds, it is idle. Okay, and again it started sending 2 Mbps per second again. That is here. How many? This is 1 second, 2 seconds, 3 seconds. So total 6 bits. Okay, so 6 Mbps. Okay, so per second it is sending 2 MB. So for 3 seconds it is 6 MB. So here it is 24 MB. Okay, so now how this leaky bucket is going to perform in, see, so even though it is sending 12 Mbps here and it is sending 2 Mbps here, now it shaped, the leaky bucket shaped the traffic into a constant flow. Okay, So if you see here, now per second here it is allowing 3 Mbps only. So for 10 seconds it is 30 Mbps. Okay, so if you see here 24 plus 6 is 30 Mbps. So here also for 10 seconds it has sent 30 Mbps, and now when we send this through a leaky bucket algorithm, it is going to send 30 Mbps. So that is 3 Mbps per second. So after 10 seconds it is also 30 Mbps. So this is how the leaky bucket algorithm is going to shape the traffic. Okay. గైస్ అర్థమైంది కదా లీకీ బకెట్ అల్గోరిథం గురించి.
Yes, sir.
So if you see, this is our leaky bucket algorithm. So the packet is going to arrive here. Okay, if the queue is full, obviously it will discard the information. If the queue is not full, they are filled in the queue. Okay, so if you see, the leaky bucket algorithm is going to remove the packet at a constant rate. Okay, so whatever may be the input from the sender, okay, when it is passing through this leaky bucket algorithm, it removes the data at a constant rate only. Okay, so the processor processes and it sends the packet to the out of the network or to some other destination. Okay, so this is how leaky bucket implementation is done. Okay, so finally, if you see it, the leaky bucket algorithm shapes this bursty traffic into fixed rate traffic by averaging the data rate. It averages the data rate. So if the bucket is full, obviously it will drop the packet. It cannot see. If you see here, so if this bucket is full, obviously the water flows out of this bucket, isn't it? The same happens with the algorithm also. Okay. So this is a leaky bucket traffic shaping mechanism, and the next one is token bucket. So coming to the token bucket. So before discussing about token bucket, if you see in the leaky bucket algorithm, the leaky bucket is very restrictive. I'm talking about leaky bucket, not token bucket. Okay, the leaky bucket is it is very restrictive. So it does not give any importance to idle host. If you see here, this for this amount of time, the host is idle. That is, if host is not sending any data for this amount of time, the bucket becomes empty, obviously, right? So because it is sending a fixed flow here, if the host for this 5 seconds, if it is not sending for some amount, after some amount of time, this bucket becomes empty. Okay. So now again, if the host is having again a bursty traffic, okay, if it is having a bursty traffic, again the leaky bucket allows again on an average rate only. Okay. So the time for which this host is idle is not taken into account. But coming to the token bucket algorithm, if you see in the token bucket algorithm, the host is this algorithm allows the hosts which are idle to accumulate the credit. That is, let us say, initially we have one first second to 10 seconds. Okay, so for 1 to 3 seconds, the host is sending the information, so there is no problem. For 3 to 8 seconds, it did not send any information. No, the when we are implementing the token bucket, so this amount of information it can take some tokens. Okay, so it can take some tokens from the algorithm. Okay, and it can send the bursty traffic later. I'll just explain you with an example. Don't worry. Okay, so if you see here, for each tick of the clock, the system is going to send n number of tokens. Okay, so this is our bucket. So for one token added per tick. Okay, for one tick, we are going to add one token. That is here n is equal to 1. So for a clock tick, we are going to add one token to the bucket. So the system can now send the information until it does not have any tokens in this bucket. That is, let us say the system is having some 10 tokens. Now the system, if one token is for sending 1 megabyte, so the system can now send only 10 megabytes. If there is no token in this bucket, the system is not, the source station is not able to send the data. Okay, so I'll make it more clear. Okay, so for every byte it is sending, for every byte the system is sending, it removes one token here. So if you see here, one token is removed and discarded per cell transmitted. That is, one token will be added per tick and it is added to the available tokens. Now, for every transmission, one token is removed. So only data is transmitted until the tokens are available in this bucket. Okay. So let us say, for example, if n is equal to 100. What is the meaning of n equal to 100? Per clock tick, how many number of tokens will be added? 100 number of tokens will be added here. Okay. So for let us say for 2 seconds, now the system can send how many number of bytes? So per second it is adding 100. So for 2 seconds, 200 will be there. So now the system can send 200 bytes of data. So after that, it cannot send the data if this bucket is not going to have a token. Okay. So in this manner, here the host can send bursty data. See, if here in this leaky bucket algorithm, the host cannot send bursty data. So here, as long as the tokens are available, that is, as long as the bucket is not empty, the host can send the bursty data also. Okay. So here, if you see again, the packets arrive. If the queue is full, obviously it will discard. If it is not full, then it is processed. So how it is processed? One token will be removed at a time, and for each and every packet sent, or for each and every byte sent, one token will be removed. So here the token bucket can be implemented with the help of a counter. Okay. So initially the token is initialized, the counter is initialized to 0. That is, there are no tokens, so the system cannot send any data. So each time for this bucket, a token is added. Okay. And the counter is incremented by 1. So 0 plus 1 is 1. Okay. So for each time a unit of data is sent. So here one token is there. Now the sender can send one unit of data. So one unit of data is sent. Again the counter is decremented by 1. That is 1 minus 1 is 0. So the total number of tokens now after first data transmission is 0. So like that, as soon as we have tokens in the system, the system can send the information. So only until the bucket is having tokens, then only the system can send the information. The system cannot send the information if the bucket is not having any tokens. So here the token bucket allows bursty traffic at a regulated maximum rate. Okay, here also we are telling that actually this is a traffic shaping technique to avoid the bursty traffic, to that is to reduce congestion, right? So here it allows, the token bucket allows bursty traffic, but at a regulated maximum rate. Okay, it depends. It takes and it regulates at a maximum rate only. Okay. So this is how we have token bucket working. Okay, and the last thing is resource reservation. Resource reservation means, so obviously whenever the data is flowing to the network, it requires resources such as buffer, bandwidth, the CPU time, and so on. Right. So the quality of service is improved if these are reserved before. Okay, isn't it? If the buffers are reserved and if the bandwidth is reserved and if the CPU time is reserved, so obviously the quality of service will be improved. That is, before sending the data only, if we reserve the resources, the quality of service will be improved. And the last thing is admission control. What is admission control? It is a mechanism which is used by the router, or you can take a switch. That is, whether the router or switch accepts or rejects a flow based upon some predefined parameters. That is, either this router can accept the flow or it can reject the flow based upon some parameters. That is, before accepting a flow, so the router may check for some specifications, that is in terms of bandwidth, and then you may take buffer size, okay, and then you may take CPU speed, etc. So basing upon these availability, now the router is going to take a decision whether to accept the flow or to reject a flow. So this is what we are going to call it as admission control. Okay.